Okay, let's jump to this one, the second, which is some kind of composite expression using complex numbers. It's just a combination of those things we've been doing. It's like performing a division, then constructing the complex conjugate, and also some potency of J, perhaps using the periodic cycle of results that you have seen probably when talking about this. This is an interesting thing by itself. Perhaps we should have a look at it. Yes, I make a little jump also here, because later we have these circle division cases where the exercise 2.4, the second, is interesting because the equation z power 4 minus 1 equals 0 turns out to be the equation that defines the so-called fourth unit roots, or also fourth roots of unity. You know why it's called the fourth roots of unity? It's just because, oh, where is it? I had it written here originally. So if you change this, the setting, then you have z by 4, power 4, equals 1. And now, if you say, to solve this equation, I need to find all numbers z so that these potentiated by 4 results to 1. So in other words, to solve this equation, you have to take the fourth root to get rid of this exponent 4. And since you do that, and since you find 4 different valid solutions, we talk about these being the fourth roots of unity, the fourth roots of the number 1. That's what it means, right? From school, you know, you could get 1 and minus 1, 1 and negative 1 as a result for this equation. But still, 2 of the solutions would be missing. And by inventing, or yes, by discovering complex numbers, we find those missing 2 other solutions, which are now called j and minus j, which is the opposite of j, right? The opposite number. So, but with a different perspective, we can say, what happens if we take 1 and then we potentiate it by 2, by 3, by 4, and we see nothing happens. It just stays what it is, 1. If we do the same thing with the number minus 1, we find it always jumps here back and forth. When I take it, minus 1 squared is 1. Minus 1 by power 3 is again minus 1. And so it jumps back and forth. But what it actually does is it turns around every time 100 degrees. That's the funny thing about it. You can say the 1 turns makes a full turn every time you multiply it by itself, right? The minus 1 turns around a straight angle every time. And now our new imaginary number j has its own way of turning around by potentiating. It always turns around by its own argument. Its own argument is p half, you know? So j to the power of 2 results to this right angle added is another right angle, means we have the direction to the left, which is the negative 1. And that's the definition of j, the implicit definition. J squared is negative 1. If I take j to the third, then I have another right angle to add here, and it shows downward. And it means that j to the third is minus j, which is also clear because minus this minus sign can be replaced by j squared itself. So j squared times j is j to the power of 3. So that's very consistent. And also j to the power of 4, then of course is 1 again. Now, which can also be written as, if you want, j squared, j to the power of 4 is of course equal to j squared times j squared. So it's minus 1 by minus 1. And this is all very consistent. That's the, well, that's the point about complex numbers. So you get consistent results. using our ancient calculation rules by just inventing a number which square is equal to -1. A number to which the square is equal to -1. So anyway, and this means if I potentiate further and take j to the power of 5, I get, this is a cycle, and I always go through this cycle because this one is can again be written as j to the power of 4 another times j. So that means since this is always 1, it means it's j again. So as soon as I reach the 5 in the exponent, it starts with j again, and it goes around, around, around. So that's the cycle of potentiating j. That's what I wanted to explain as a side note. And now back to our exercise 2.1b, 2.1.2, let's say. So in short, I just take this fraction here, okay? 3 plus 2j divided by 3 minus 4j. I do, yeah, this is well known. I multiply on both sides. So I multiply with the complex conjugate of the denominator as before. I've done it before, okay? And the same thing happens in the numerator, so that it cancels. So this is like if I would multiply by 1 the whole fraction. So in down here it's always the same. It's like by the third binomial formula, I get the square sum of the components. So that's 3 squared plus 16 plus 4 squared. It's again 25 like before in the other example. But this time I have to multiply this by this by combining all the different constituents. So I have 3 by 3 is 9. I get 3 times, I want to say 3 times 3. 3 times 4j is 12j. Then I have 2j here times 3, which is another plus 6j. And I get 2j multiplied by 4j. So that's 2 times 4 equals 8, but 8 times j squared. And that's why the plus 8 becomes a minus 8. Yeah, okay, I replace j squared by a minus sign. So altogether, I have 9 minus 8 for the real part, which is 1, and I have 12j plus 6j, which is 18j for the imaginary. And mathematical speaking, the imaginary part of this number is 18, okay? But 18j is the imaginary, contribution to it. It's sometimes a little dangerous you shouldn't forget that the so-called imaginary part always denotes the factor that is taken for j, not including the j, okay? So the real part and the imaginary part are real numbers. They're just the factors that you find inside here, okay? So anyway, now this is what we get. Then the whole expression says we should take the result times 25. So if I do this in the end, this 25 cancels against here 1 by 25. So that disappears again. So what remains is this one, 1 plus 18j. Then we have to do the star to perform the complex conjugate, and then to add 18j power of 5. Now that's all. And 1 plus 18j star, of course, means that I replace j by minus j. So I get 1 minus 18j plus, and then we said that j to the power of 5 is the same as j to the 4 times j. This is 1, and so it's just j. You can just cross out the exponential in this case, the exponent. So it remains 1 minus 18j plus 18j. This again cancels each other, so it stays the number 1. That's the simple result of this expression. This is just a just an exercise to get accustomed to well, to changing terms using complex numbers. So that's it.
Excuse me, there is one question. Where did 1/25 go? 1 divided by 25?
Where did what go?
1 divided by 25 in the first row.
So that disappeared because from here, starting from here, I just took this fraction. Okay, I extracted this fraction from the whole expression and tried to simplify it. And when I simplify this fraction here,
I see. I forgot.
I get this one, and then afterwards, only afterwards, I take the factor 25 into play. Okay, so I insert this expression for the fraction here, and that's when 25 times 1 by 25 cancels out.
Yes, thank you.
Okay, so there's nothing else than 1 in the end, right? Well, I remember in Martin's note I saw the section where he compares quadratic equations of different sort, as I always do the same in the German course. And in this exercise, you see a nice, a comparison of the well-known 3 cases, which you all know from school. There is a case where you have discriminant positive, discriminant 0, discriminant negative. And let's just look. So without okay, I just good idea is to bring this to to normalize it, so that the leading coefficient is 1. That's a good idea anyway. And so this is what I'm doing, and it results in z square plus 2z plus 1 only, and then this is strikingly binomic. You know what I mean? So it's suddenly clear that by the first binomial formula, this is an expression which must have resulted when we use the first binomial formula. So you can just put it in the form z plus 1 in parentheses square equals 0. I'm doing that because I don't really like this well-known solution formula for quadratic equations. It's nice, but it's too complicated. It goes much easier in many cases. So this is the way. And now if I take the square root, of course I must allow for positive and negative squared because it's a quadratic formula. So that's just my sign for saying I take the square root on both sides. So which means it results in z plus 1 equals 0, but there is no, this plus or minus. These 2 cases don't really deliver 2 different solutions because we take the root of 0. And that's why in the end, we get only 1, but as we always say, a 2-fold solution, which is -1, it seems. Right? So that counts as a 2. Do you say 2-fold? The multiplicity of this solution is, I think, is it called multiplicity? Can somebody help me? We talk of a multiple solution. Multiplicity. It counts twice because it's like regularly you would have 2 simple solutions, but in this case you have 1 double solution. That's but there must be a special term for this in English, and I'm not quite sure if it's called multiplicity. I think so. Multiplicity of 2. It's like a touching point of a graph between the graph of a function and the x-axis. You know what I mean? A touching point, which is also a 0. And this is always a sign. If the graph touches the x-axis instead of intersecting it, it usually is such a double solution. I hope you know what I'm talking about. Okay. If you know the correct special term, you can tell me. So in the second case, I do it like this. This shouts to me, I'm easy. It tells me, if I look at it, I see it can be solved by guessing, or better speaking, by using the famous Vietus Theorem. I hope you know it. The Vietus Theorem is quite simple. It takes the following idea. So that's done, okay? That's it. It's a real negative but real solution which counts twice. So the reason behind is because the so-called discriminant, which you all know of this equation, D equals what? Who knows it?
Equals 4.
1 second. I'm talking about this, you know, this from school, it's the X formula, but Z, which is the ABC formula, right? Which is minus B plus or minus square root of, you know, B square minus 4AC, and then divided by 2A. Is that right? I think so. And then only if the term under the root sign, so the radicand, do you say radicand? I think so, yeah? So this term is called the discriminant, because if it's positive, you get two different solutions. If it's 0, you get one double solution, and if it's negative, you don't get any solution at all in the real domain. So I think you answered 4, but there was a misunderstanding, probably. Because the discriminant is not equal to 4 in this. Are you looking at this case? Perhaps. I was talking about this case. And here the discriminant must be 0, definitely. And that's the reason why we get a double solution. You agree? I think you can test it, okay? Let's test it. B is 2. This is the coefficients, A, B, C, right? B is 2, A is 1, C is 1. So I have 2 squared is 4, and 4 minus 4 times 1 times 1, so 4 minus 4 is 0. So I have square root of 0, and that's why this plus or minus distinguish, we try to distinguish these two solutions, but in the end, this distinguishing these won't work. They fall together, and that's why they count twice. So anyway, Vietus theorem. It's so easy. Just imagine you have a product form of a polynomial, of a squared, of a quadratic polynomial, which means that you have put it in this form where you have one linear factor and another linear factor. The product of these says by the theorem of zeros that if this gets 0, everything gets 0, and also here. So that means that the two solutions of this, I must say equals 0, that's it. The two zeros of this equation then are x equals a and x equals b. So, but if I remove the brackets again, I get x times x is x squared. I get minus, in parentheses, a plus b times x and plus ab. So that's why if I have integer solutions, these integer solutions must be factors contained in this constant. Okay, because the constant is always AB. The constant is the product of all the zeros. The 0, you know what I mean, 0, okay? Is A and B. So I can guess it. I can guess something like plus minus 1, plus minus 3. These are the candidates for integer solutions of this equation. Okay, and then I just test if the sum of my two solutions is the negative value of that linear coefficient. So my trick is this. This is Vietus theorem. I say supposedly -1 and -3 are the solutions. If so, the product of -1 and -3 is 3, right? So that fits it. And the sum of -1 plus -3 is -4. And here, the linear coefficient is 4. So everything's fine. And that says suddenly, without any solution formula, I can conclude that the two solutions of this equation are -1 and -3. If you don't get this, do it your way. It's no problem. You can also use completing the square. It's a very, very good method. Anyway, there are so many special methods which I like to show from time to time. So I did. I don't believe it. The time is over. It's just a shame, but not so tragic, I think, because we can always go back to our topics next time, and then I think we soon will be in a good rhythm. So what do we do for now? Because my other boys and girls are already joining us, which I didn't even notice. What do? We have remaining this one, just conversion between Cartesian and polar form, back and forth. That's quite nice, and I think you'll make it. Anyway, I will upload the sessions and also this file very soon, so then you can just read after the solutions which I have already put in, not all of them, but some of them. And then we have the fundamental theorem, complex roots, completing the square. There, the second one we've already solved together, yeah, in words. The first one is something nice for you because you just take c to the power of 3 equals -j, and then you try to take the third root by using the circle division method. And then here, that's the most, that's no question, that's the hardest of all. But it's I have a solution inside here which is very detailed, and I even present you a graphical solution. If you take the time, and I must say there are some really ugly numbers inside, but in the end, it's a very nice graphical view to understanding these solutions in the sense of a division, dividing the circle. Also, even for this last exercise. So sorry for well, for not keeping the time schedule, but anyway, thanks for coming. Questions delayed to next time, okay? And then have a nice week and see you.
Sure, thank you.
Thank you, Professor.
Thanks, bye.
Thank you, bye.